if we take a look, open this real quick. There it is. If we take a look, we know that the pressure outside, the atmospheric pressure, is higher than in here, not by too much, but by 42. So that means that this is lower pressure in here because that liquid has been forced up into it. So we have 691 millimeters of mercury. And I believe we talked about how atmospheric pressure is basically like a dog pile in a football game. More particles on top, all the way up to space, are going to cause 14.7 pounds per square inch if you are at what we call sea level. And that's the force of the gas particles colliding with everything and you. How do we measure atmospheric pressure? We use a barometer, which is basically a tube that, just like this, atmospheric pressure pushes down on it, and then we can take a reading on there. Is atmospheric pressure the same everywhere on Earth? Actually 2 days ago, I told you about the time that me and my friends, we went up the mountain in Hawaii, and we noticed that pressure was a lot less up there. We had some potato chip bags pop and expand. And then as we went down, we saw bottles of water that we had closed up at the top. Basically, their volume decreased. As the pressure around them got higher. Cool. All right, let's move on to kinetic theory of gases. There are 4 assumptions with the kinetic theory of gas. If we take a look here, make sure I got everything good. All right, so the 4 assumptions for the kinetic theory of gas. Bring it down a little bit. Actually, I'm going to bring this up a little bit. That'll help. All right, so all particles and matter in constant motion. You learned this last semester. We talked about solids, where the particles are very close to each other and organized. The only motion you have with solids is basically vibration. For example, if you hum and you hum near the desk or your whatever, or you hum near your hand, you can feel those vibrations. Or if we beat, we can hear those vibrations and we can see those vibrations. If we have particles that are not so tightly packed together, they can move around each other. These are fluids. This one is a liquid. The particles are close together, but they still have enough room to move around each other. So we have particles that are stuck and only vibrating, particles that can move around each other, but are close together still. Those are liquids. And last but not least, we have gases. Gases, the particles themselves are very small compared to the space between them, which is far apart. Right here, these particles are going to have interactions with each other. They're going to attract to each other. Like water, for example. Water tends to stick to itself, right? Together. That's why it comes in water droplets. Or solids. Those are stuck together so much that they can't even move. Gases, not a lot of interactions between the particles themselves. So this has 2 consequences. The first part means that we can compress a gas. The second part means that a gas will expand to take the shape of its container. If I release a gas in this room, it will move about the entire room. It will take the shape of its container, which is the room, right? Third, the particles move rapidly and in constant random motion. They move in straight paths independent of each other and change direction only upon collision. So if we take a look, there is a game. Does anybody know this game? Where you have a table? Christian's got is pool or billiards. So you have a ball. What's that?
Hungry hippos.
Yeah, or hungry hippos actually works the same because the balls are all colliding, right? So they bounce in all these straight line patterns. That's how you sit there and then you open it up. But if we take a look, if we hit this ball into this ball will collide, then it will collide again, and it will move in a straight line pattern. If we don't put English or spin it or anything. But if we hit it directly, boom, boom, straight line pattern, and the collision is perfectly elastic. That's why you want to make sure that you have a nice brushed felt on the pool table, because that reduces friction. If there's too much friction, then the ball hits and then it doesn't go as far because it loses that momentum. But in gas laws, we assume that they're all perfectly elastic. If we take a look, this is called a Newton's cradle. I'm going to switch to the other camera so that you can see the Newton's cradle. You should go to full view of me. And if we take a look, we pull one ball back. An elastic collision makes one ball go forward. If nothing hits it, they stop. When it hits, one ball goes forward because of a perfect elastic collision. If I pull two balls back, two balls go forward. We are conserving the momentum here, right? Perfectly elastic collision, they collide. We have the momentum of two balls go forward. If I pull three balls back, unfortunately, I don't have three balls on this side, so we can't do anything there. But if I pull one ball back on each side, perfectly elastic. If I pull two balls back on each side, perfectly elastic. If I pull three on one and two on the other, well, I don't have three balls on the other side. What do you think might happen, though, if I did have three balls on this side and I pulled three back? Well, following everything that we've done, if I had three balls on this side and three balls on this side and I pulled three back, then when that hits, three should go forward. Three should go forward. What do you think would happen if I did it right now? I mean, yeah, go ahead.
I don't know.
Yeah, right? We can't really do it because we don't have three balls on this side. Somebody typing in what might happen? Nope. All right. So these are perfectly elastic. 1 and 1, 2 and 2. Well, we don't have three, so let's do just 1, just 2, 3. Well, we don't have 3. Does anybody want to try it anyway? No? All right.
If you have 3, want the middle one, just continue moving with the other 2.
Let's try it. Who's that? That's
Henry Dayford.
good, good. Let's try it. Oh, looky there. So it still is perfectly elastic. We still have 3. If we do 4, well, using the same idea, we should get 4 to move as well. What do you think then if I do 3 and 2? Well, look at that. Still perfectly elastic. We're still conserving that momentum. Very nice. So problems do occur with this if our particles get too cold. If the particles get too cold, remember, they're going to condense. And that means that they're going to get closer together, which is going to cause them to interact with each other. So that's no good. High pressure, well, if I put something under high pressure, I've compacted it. So that's also going to cause them to get closer, where they may undergo interactions, which is also no good. So keep that in mind. We do have limitations for this: low temperature and high pressure. All right, so standard temperature pressure. Scientists decided to make something. They were like, okay, let's make something that everybody can have for their laboratory. What's a temperature that everybody can obtain? Well, 0 degrees Celsius can be obtained if you have ice and water. You can make what's called an ice bath. If we recall from Monday, to get from Celsius to Kelvin, we add 273. So 273 Kelvin, or 0 degrees Celsius, is the standard temperature that scientists determined. Scientists then said, well, can we make a standard pressure? Well, they knew that above the Earth, it had 1 atmosphere, but it only measured 1 atmosphere, or 101 kilopascals, at sea level, because then you had exactly 1 atmosphere above you. And that does change a little bit with wind, but if you may take out the wind by building a building that is not affected by it, you could get really close to 1 atmosphere, which we said is 760 millimeters of mercury. So there we go. There's our standard temperature and our standard pressure. And that's what scientists base things on. They sit there and go, well, what would that be at standard temperature and pressure? Right? What would the volume of this balloon be at standard temperature pressure? Currently, it is at what temperature? It's not 0 degrees in here, even though sometimes it feels like it. So it's a little warmer, right? So scientists might say, okay, well, what's the standard temperature, and what would this balloon look like at standard temperature? Let's talk about balloons then. Let's go on to this activity. What keeps a balloon inflated? So if I blow up a balloon, if I let that gas out, the balloon gets smaller. If I tie that gas off, what keeps this balloon inflated?
The pressure on like the inner walls being exerted.
Good. Lucille, Lucy? So if we take a look, the pressure from the gas particles colliding with the inner wall. I think you covered both questions there. So pressure keeps the balloon inflated. What is pressure caused by? From the gas particles colliding with the walls of the balloon. Good. We know if we have a hole in this, then the particles will just fly out. Now this balloon is, as a kid and we had parties or whatnot, we would always sit there and my mom would buy this stuff. It was just called like cola, or they would have like lemon soda or whatever. But they would always come, instead of your 2-liter bottles like Dr. Pepper and like the stuff I liked, they would always come in 3-liter bottles. So I'm going to say that this looks about like the size of those 3-liter bottles when I was a kid. This is about 3 liters. It's a little bigger than 2 liters. I think it's between 3 and 4 liters probably. So I'm going to say 3 liters for this. Remember how many particles are in 1 mole? This is one of those that's easier to say than to type out probably. How many particles? 1 mole equals how many particles? What was that one?
600 sextillion.
Yeah, there you go. I was wondering if you were going to give me the scientific notation. Good job. You didn't bother, but we would have also accepted 6.02 times 10 to the 23rd, which is 602 sextillion, right? That is particles. A lot of times in here we used particles instead of saying atoms or molecules, because particles covers both of those things. Well, 1 mole of any gas at standard temperature and pressure takes up 22.4 liters. Now let's imagine that this room is standard temperature and pressure. I want to figure out how many particles are in this balloon. So I know the volume is 3 liters. And I know that every 22.4 liters is 1 mole. And I know that every 1 mole is 6.02 times 10 to the 23rd particles. Liters cancel out, moles cancel out, leaving me with particles. So in my calculator, I start off with what I know. I know 3 liters. I know that 22.4 liters is 1 mole. That goes on bottom, or I divide by that because I want liters to cancel out. Moles If I stop now, I've got moles. I don't want moles, I want particles. So every 1 mole is 602 sextillion particles. So that's on top because moles needs to cancel out. So I multiply by 6.02. This is important. Watch carefully. I want to make sure everybody knows how to use this E number. So I hit second and then that E. I don't hit times E or times 10E or anything. It's just 6.02 E, 23. When we hit enter, I get 8.06 times 10 to the 22nd particles. How big is that? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So if we take a look there, it's 80 sextillion particles. This is why we have scientific notation, so we don't have to take 45 seconds to write out a number. That's a lot of particles in this balloon, right? What if I did not tie this and I put more particles in it? What would you see?
The balloon would expand.
You got it. Volume gets bigger. More particles would mean there's more particles bouncing off the walls, would cause the balloon to expand. Here's an interesting thing. We know that the pressure in this room is set. When we blow up the balloon, we create a little higher pressure in here, which causes the balloon to expand. But then eventually the pressure inside and outside has to become equal. Otherwise, the balloon would keep getting bigger or would get smaller, right? So we set the number of particles in this balloon since it's tied. If I squeeze the balloon, does the number of particles in there change?
Nope.
No. The only way that we could change the particles is if there were a hole in this balloon. So if I squeeze the balloon, the number of particles remains constant. So right there where it says particles, and I know that you might not be able to see this, but it says remain constant. I'll go back to that after we do a few more of these. So if I squeeze the balloon, what happens to the volume? Somebody squeezes your chest, does your chest get smaller or bigger or stay the same?
Volume changes.
The volume changes when I squeeze it. If I squeeze it a lot, I mean, the volume still changes, but it's less apparent because the balloon can move, right? But definitely when I squeeze it, the volume goes down or decreases. When I squeeze the balloon and the volume goes down, what happens to the pressure?
It increases.
Good. So squeeze the balloon. We know if we squeeze the balloon too much, the pressure will get too high and the balloon will pop. If I squeeze the balloon, the pressure goes up or increases. Imagine if I had a balloon squeezing machine. What's the temperature of this balloon? Where's the balloon at? Where is this balloon?
Is it room temperature?
You got it. It's in this room. So this balloon is at room temperature, right? Imagine if I had a balloon squeezing machine, what temperature would the balloon squeezing machine be at? Where is the balloon squeezing machine?
In the room.
In the room. So it would be at room temperature. If I put the balloon in the balloon squeezing machine and the machine squeezes it and both of them are at room temperature, will there be any change in temperature? No.
No.
Right? There won't be any change in temperature. Why can't I say the same thing about my hand squeezing it?
Your hand has an exothermic effect on the balloon.
Got it. My hands are going to give energy to the balloon, right? So if I squeeze this with my hands, yes. If I have the balloon squeezing machine, the temperature will remain constant. So if the volume goes down, pressure goes up. If the volume goes up, pressure would go down. We call this indirectly proportional or indirectly related. They're indirectly related. This P1V1 for P initial, V initial is equal to P2V2, P final, V final is known as Boyles law. It relates pressure to volume. Let's take a look at how we can observe this in another way. A balloon is nice. But take a look here. I've got a syringe. If I start the volume of the gas in there at 20 cc's, since this is open, the pressure in here is equal to the pressure out here. I'm going to then close that so that the volume is now 5 cc's. So I decreased volume. The pressure should go up. And you can hear that. When I release that, pressure from the inside goes to the outside because it's higher pressure in there. Higher pressure always goes to lower pressure. Whenever you have a tire pop, the air inside the tire goes to the outside of the tire. If we take a look here, let's say I start with 5 milliliters or 5 cc's, and I pull this out. Volume goes up, so pressure goes down. The pressure outside is still higher, so if I let go, you can see that the plunger goes in. Pressure out here pushes on the plunger to make it go into the lower pressure. If I do that even more extremely, it should react much quicker. See if I can do this with my weird hands this way. Boom. High pressure out here pushes that in. That is known as Boyles law. So, that is the basics of it. If you do get some time, you might take a look at some of the demonstrations on here. But after that first demonstration, I basically go back and do exactly what we did today and a little bit further. This is a video. This might be worth watching. This is Boyle's law. Let's see if I can make it big.
Robert Boyle, an English chemist, studied the relationship between pressure and volume of gas. This apparatus demonstrates his findings. Liquid is in the syringe and tube, and air is trapped in the rest of the sealed tube. When pressure is applied by the syringe, the volume of air decreases by a proportional amount.
Pressure goes up, volume goes down.
This is a demonstration of Boyles' law. It states if the temperature and amount of a gas remains constant, the volume varies inversely as the pressure changes.
So there we go. That's what we wanted to accomplish today. If you have any questions, you're more than welcome to stick around. There is no homework tonight other than if you need help with that, obviously go and watch some of this video. I do show a gas apparatus machine, which is kind of cool. You do have 22 minutes left. So if you wanted to look at this, by all means, go do it. Otherwise, if you did not get the homework done from yesterday, which would be the Mythbuster, please make sure you go through and watch that Mythbuster so that you can see how pressure and atmospheric pressure and pressure underwater affect anything. If I took this balloon at this volume underneath the water, every 30 feet I go down is another atmosphere of pressure. So that means that as I take this balloon down, it would get smaller and smaller and smaller because more pressure would be on it. It's kind of cool. Have a great day. Take care. If you have any questions, by all means, stick around. Otherwise, get out of here.